Good afternoon and welcome back to CS 240. We've been on a journey where we have talked about how to go through a number of different system foundations. We start all the way back with data, and we've moved through the CPU, we've moved through memory, and we briefly talked about peripherals. We are now talking about the operating system. And as we begin to talk about the operating system, we're going to sort of begin to talk about individual apps. Because ultimately what I think a lot of you guys will be doing is you guys will be app developers. So we have finished up talking about synchronization and how we have multiple threads that will sometimes need to do a task together. And what we'll go from there is I want to talk briefly about this idea of threads versus processes. So processes in a modern context, you can almost think of these as individual apps. And what we're going to talk about is what is the difference between threads and processes, maybe. All right, so threads are going to share, threads within a process share nearly everything. So the key idea that we have talked about so far is the idea that threads need synchronization because they share the same memory. We saw the idea that they share all of the same memory addresses except for they share the same memory addresses. The only private space they have is their own stack frame. And on the other side, we have not really talked much about processes. But processes are almost completely isolated from other processes. So the idea here is that when you have two different apps running on your computer or on your phone, these apps don't talk to each other. When you have a version of Chrome that's open and a version of Microsoft Word that's open, these two apps are completely independent apps. They're doing their own thing, and you don't want one of them being having really crappy code to crash the other app or to crash your entire phone or to crash your entire computer. So we have the idea that we have a very little amount of isolation. Are you looking for the handout? They're right up here by the door. So if you're looking, so you have this idea that threads are extremely shared. They have lots of resources they're sharing. And you have processes that are nearly completely isolated from each other. And we can look at the different trade-offs between whether or not we as programmers will want to use a thread or want to use a process. So I have a little table that we're going to talk about that talks about what about individual threads versus individual processes. So we've talked about how do you create a thread. So in MP4, when you're doing the resource wallet, and all the examples you've seen in lecture, how do you actually create a thread? What's the library call we use? How do we create a new thread in C? I heard one of you. I think that's right. What did you say? pthread create, yes. pthread create is going to be the command you write in C to actually create a new thread. So you create one with pthread create, and I'm going to say it is extremely fast and cheap. It doesn't use very many resources. It gets done extremely quickly. It's easy to create them with one line of code, very, very quick, because they share a bunch of resources. There's very little you have to actually copy over or create. On the other side of the universe, creating a new process is actually quite hard. It's also done with one line of code. So you actually create it with the command called fork. So what fork does is a really unique system call. What fork does is it actually returns twice. So it works completely different. Fork returns twice. Once as the parent, and once as the child. So the idea is when you want to create a new process, you actually don't create a new process by saying, hey, go run this other code. The way you create a new process in C is you actually create a clone of yourself. The actual underlying system call is actually called clone, not even called fork. Fork's the library call we see in C. But you actually make an identical copy of yourself, and then you have your program counter for both processes set to the exact same line of code. So it looks like fork actually returns twice from our point of view. We have it return once in the child and once in the parent. So the parent forks, it clones itself, it now has itself and a new child process. Because it has to copy itself, its virtual page table, everything about it, this is slow and expensive. So it takes significantly more time to create an entire copy of yourself than it does to just create one thread that's an extra function that you're going to run at the same time. And of course, when you clone a process, you are going to clone that thread that you're currently in. So you're creating a new thread and a new virtual page table and all sorts of new stuff. So that is the first thing, is the creation. Second thing, we've kind of talked about it, overhead. The overhead of a thread is going to be small. The only overhead you really have for a thread is you're going to have a separate program counter, a separate thread ID, and registers. So you have a few things, like the program counter, like the actual thread identifier that identifies it, the CPU registers, the local variables, your actual running code, that's all shared on or not shared between threads. But the amount of overhead is quite small. On the other hand, two processes have quite a large overhead. So we can talk about all the things that are shared between processes. This is your virtual page table. So your page table is shared. Or sorry, your page table is not shared. So you have separate page tables for each process. You have an entire thing called the process control block. Or the PCB. So this process control block contains all of the state information to deal with your process. This is big. Process control blocks in some systems take an entire page of memory. So that's 4 kilobytes of data that you have to maintain just to maintain a process. So it's going to be much, much more expensive to have a process. The third thing we might want to talk about is context switching. So context switching is the idea that how much does it take to change out the CPU from running one thread to another thread versus changing out the CPU from running one process to another process. Context switching between threads is fast. Context switching between processes is slow. And virtual memory, shared between threads, it's private between processes. So in all of this universe, so we have all of these threads that have all these shared resources. Threads are extremely fast. Threads are extremely efficient. We love threads. Processes seem like we're hating on them. Why in the world would we ever want to use a process? Yeah. Oh yeah, private virtual memory. I may not want to have you creeping on my code, right? Or my memory addresses. Yeah, so the big advantage for processes is we get security. And I'm going to put it in security and isolation. So if we want and this is something that's really worth a lot. I don't want my crappy code crashing your amazing code. Like when you've written this beautiful code like your malloc allocator in MP3, I don't want our code to crash your code. So I want isolation. And this is actually something that's happened in the past few years. that is this great divide between these really fast threads and these really slow processes. So if you think about Chrome, how many of you guys have like at least 10 tabs open on average? Yeah. So all of those tabs have a bunch of things running in them, a bunch of JavaScript code, right? And how much do you trust the JavaScript code that's running on various different websites? Probably like not at all, right? You're probably not going to trust the JavaScript code. So what used to be the case is we used to live in a universe where every single window of Chrome, no matter how many tabs it had, was one process. So that means if I go over to my Chrome, I have no idea what's open on my Chrome right now. So let's see. So if I go to my Chrome, I've got a whole bunch of tabs open. Classic, like 15 tabs. And what we'll see is if I go over to the details, which lists every single process that's running on a Windows machine, I can see how many different processes do I have. Well, I've got some processes up here that do stuff. And then right here on my fourth process, I begin Chrome. And what do you see all the way down? Chrome, 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 Chrome. So all of those little red icons, even if you can't read it out, that's all Chrome. Chrome, 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 all the way down until I have command prompt down here in Visual Studio Code. So there's actually a really interesting case study that Google did and said, what should we do about the fact that one web page that's poorly programmed or has an infinite loop in their JavaScript can ruin the performance of the entire Chrome operating system. Or sorry, not Chrome operating, the entire Chrome web browser. Do we want one single tab to just make our application look like it's running like trash? No, we want to look like our web browser is the fastest web browser out there. We want to look efficient. Even if you have one tab that's a resource hog, we want Chrome to still be responsive. So Chrome made the decision several years ago that every time you open up a new tab in Chrome, you are opening up an entirely new process. So every single tab is its own process, so it's completely isolated from other processes. And this also gives us some security protections, where if you're entering like bank login information on one tab, but you have crappy Facebook game open on the other tab, crappy Facebook game won't be able to potentially even see your bank account information, even if there's a bug in Chrome, because they're completely separate processes. And you can see that Chrome has a bajillion processes. And you can see this is a model that's used quite a bit. So Visual Studio Code, for every VS Code uses this, because it runs on the same Chromium system, every time you have a file open in VS Code, it also opens up a new process for VS Code. Because every single file view is actually just a web page. Because VS Code is just built on the Chromium technology, the technology to build Chrome. But you have a program like Microsoft Word or something that has just a single process. So if I were to launch Word, then we'll see Word will come up. And if I find Word, we have just one process. And if we look at columns, so one thing that I know that if I do options, maybe. Select columns. So one thing I can look at is how many threads does something use? So threads, tell me how many threads you're using. So Chrome, for example, is using 44 threads right now. Or sorry, not Chrome, Word. Microsoft Word, I launched a new Word, open a new document. I've done nothing but open up Word and open up a new document. Word itself, 44 individual threads running. Chrome, ton of processes, but each of these processes have between like 8 to 23 threads, it looks like. So fewer threads per process, but many, many more processes. So that's going to be the great trade-off that you're going to have to make as a programmer. Do you want the speed of having multiple threads with the cost of not having security or isolation? If one of your threads crash, the entire program is going to crash. Or do you want the slowness of processes, but the idea that you have isolation, that if one of your processes clash, it's not going to kill your entire system? And you're going to probably find there's going to be a combination of them both that you might use. So Firefox is actually the first one to go through this model. Firefox decided to do every tab as a process first. Google was like, hey, that's a great idea. And like 3 months later, Google was like, hey, all of our tabs are processes now too. So just kind of evolution of how design ideas of what we're learning about here is actually being applied to real software. And engineers just like you are making these decisions on which style of process to use. Any questions? Yeah, Jake. Why do they make VS Code a web page? Yeah, I don't know. I mean, I think they were just like, hey, we want to render something quickly and easily. So let's build, like honestly, if you're building UIs anymore, it's really hard to find people who know how to do native UI programming. So my guess is they're like, okay, because how many of you guys have ever built a native UI application? Like you've written Win32 code or code for iOS, like native code on a system, like native windowing code. How many of you guys have ever written a web page or anything HTML based? Okay, so if I were to build a company and I wanted to build interfaces, I think I could hire 2/3 of you guys if I used web-based interfaces, right? So I'm guessing that was the engineering decision there. Is they were like, okay, I have a lot more talent out there that can do web design. And I don't know the internals of it, I just know it is built on Chromium. But yeah, it's got to do a lot of hacking to bring in like, this console is actually a web browser, so like how is it? Yeah, like there's a lot of engineering that happened there. Yeah. Yeah, so does that mean that 5 years ago, was Chrome faster and used less RAM? Yes, assuming that none of your pages acted crazy. So if every page behaved and no page infinite looped with their JavaScript or had terrible JavaScript that was loading like 1 million ads in the background, then yes, Chrome used to be faster. Nowadays, it uses more memory, but if you have one crappy tab open, it's not going to kill your entire Chrome. Because it used to be the case that if one tab crashed, your entire browser went down and you lost all your tabs. But yeah, is it more of a memory hog? Definitely. Like Chrome is like, that's my big downside with Chrome right now. Is like, after having Chrome open for like a week straight, I feel like it's got like 4 gigs of memory it's using up or something. So I sometimes will just be like, I've got to close Chrome. Cool, any other questions? So this leads nicely to the second topic, which is we have lots of different things running. And in VS Code, we said VS Code had a separate process for each tab, and the main interface is a separate process. But these processes clearly need to communicate with each other. When I open a new file, it needs to open the file. When I double-click a file, it needs to open up the correct file that's selected. There's a lot of interaction that happens between processes. And because processes by default are so isolated, we have to find a way to actually have real-time communication between processes. And this leads us to our next big topic, which is the idea of IPC, or inter-process communication. So inter-process communication is the broad terminology for all the technologies that allow real-time communication between two processes. So remember, by default, processes are isolated. Processes don't share any memory. Processes don't share any way to get information from each other. But we want to do useful things between processes. So how in the world do we have multiple processes work on a task together. Yeah. Oh, processes. Yeah, that was a bad typo. Hold on, did I make that? Yes, okay. Scratch that out on your sheet. Terrible typo there. That first sentence, between threads, cross it out. It should be between processes. Sorry, IPC is not between threads. Great catch. So sorry. Yeah, so cross it out. Make sure that sentence is correct. Between processes. So how do multiple processes communicate? They're already isolated, so how do we do it? And there's about 6 major techniques that we're going to talk about. So the first way that 2 processes can communicate with each other, even though they're completely isolated, is through the use of a pipe. So pipes are stream-based processing technology, or stream-based communication. And what I mean by stream-based communication is that you read in from one side of the pipe, you write into one side of the pipe and you read out from the other side of the pipe. You can literally think of it as a pipe where data is going in. You might write the letters A, B, C, and then coming out the end of the other end of the pipe is ABC. So whoever's writing to the pipe is going to make a call to write, and whoever's reading from the pipe is going to make a call from read. And these read and write calls are the exact same ways you read and write to a file, except for now it's a real-time system where somebody's writing to a pipe and then it immediately can be read by another process. So pipes are basically like your way to call up another process. And so anytime you're sending data, that's a stream of data, you're going to use a pipe. And you've probably already used a pipe in your life before. So if you've ever typed a command in the terminal that had this line, this straight line, this OR symbol essentially, that is the symbol for a pipe. And when you use a pipe like that, what it says is you want standard out of the first command to be given as the standard in of the second command. So you're saying, I want to put the output of my first command as the input into my second command. And I'm going to do this in real time. So these programs are actually running simultaneously. And as soon as the first command generates output, it is fed as input into the second command. And you could even chain this again. And it's going to just keep chaining our inputs and outputs together in real time. So you can have one thing that outputs a bunch of stuff, and then it goes to the next thing. So for example, if I were to go into VS Code, or into my Linux, and do ps minus aux, what ps aux is going to do is it's going to, let's get rid of this. So ps aux is going to list all of the processes that are currently running. So here is the 5 processes currently running because it's just my little WSL virtual machine. It could be a little more interesting. Hello. No, I don't want photos. I want putty. Thank you. If I go to linux.ews.illinois.edu, which you guys may be familiar with. So if I go here and do ps minus aux, I can see every single process that's running on this machine. And let's make this somewhat visible. All right, so what we have is we have every single process that's running on this particular Linux box. So we can see there's a whole bunch of people's net IDs that, actually, there's not many people on this. So hello, YAMSANI2. You are running, looks like VS Code. Awesome, good job. Running a bunch of different software, oh, okay, they're running, looks like it's just me and like one other person on this. Yeah. Hey, it's not a crazy box, it's not a crazy time to do MPs right now. There's only 2 people on the EWS box I got. And I can list all of the people and all the processes they're running, and I find all the information about all of these processes. And what's actually interesting is a stat column. This is actually whether or not that thread is currently blocked, or that process is currently blocked or not. So S is in a suspended state, which is basically a block state. So you can see most of these processes are just waiting for some event to occur. They're suspended. There should be an R somewhere. Are any of these processes, this is not a busy, oh, here we go. So this one's R. So this process is in the ready state. That process is waiting for the CPU to be available to run. So this ties back into the idea that we have these processes and threads that are in the ready state, or the block state, or the running state. So we've got these different states the processes are in. So when I do PS minus AEF, I get every single process running. But I may not want all that information, so I may pipe this command to grep, which grep is a command that says I want to remove all lines from my output unless that line has a match for a particular substring. So I want to only know which commands is WAF running. So if I do PS minus AUX, pipe grep WAF, that's real time sending all of the output from PS minus AEF, or AUX, sorry, to grep. And then grep's going to say, okay, that command has WAF, so it's going to keep that line, and it's actually going to color it for me. So I was able to take this entire list in real time and reduce it down to just the bits I need. And PS is a program, grep is a program, they're completely independent. They don't coordinate with each other, except for now we have one pipe that can help them coordinate. So that's what a pipe does, and you can always use that to chain the output of one program into the input of another program. And that's a really powerful tool that you see a lot of system people use. And we actually call that OR character a pipe character. So the other thing is we can create pipes in C. We don't have to just create them on the shell. So in C, there's just one simple library call called pipe. And what pipe does is pipe takes in a array of 2 file descriptors, and it gives you back a read end of the pipe, the write end, and the read end, so that we can send data between the two. So just to show you a little bit of code, and you have all of this code on the course website for lecture 10. So I want to just show you real fast what's going on. And one question I have for you guys, would you rather this code, so I have this dilemma that I need your help on. So I can't put all of the source code and all of the information I think you really need to know on just one page front and back. I could give us 2 pages for a lecture and include all the source code, or I could keep it 1 page and just kind of show the source code and you can download it later. Preference, thoughts? Yeah. So you're okay not seeing the entire source code printed out? Easier to see context here. Agree, disagree? Agree, don't need to print it out? Agree, disagree, Skander?
I think if you had a separate page with all the source code, that'd be nice to annotate along with breakouts.
So you're a source code fan of the extra page. All right, Aaron. So you like seeing it on paper? Okay, whose team see it on paper? Whose team just display is fine? Oh, we are pretty split. Interesting. Maybe I'll have it so you have it. I don't know. I'll work on something. So I wasn't sure. Yeah. Yeah, so I can have like an extra handout if you want it. Yeah. Yeah, and you'll always have all the source code linked. So yeah, in fact, every time, like that's one of the benefits of the kind of the workflow I set up is I want to force myself to make sure it's all ready for you. And the way I do that is I develop on one computer and I present on a different computer. So if I can't get to my own source code, it's because it's not on the Git repo. So if you're seeing source code on this computer, it's because it's on the Git repo that you can access. So there's no way for me to get here into this room and show you source code without it being on a Git repo that you can access. So that was me kind of just making sure my process made sure that you have access to the code. So you always have this code, and then the repo basically has a bunch of directories named with the number of the lectures. So let's look at the pipe .c. And what I basically do is I use this pipe command just like you saw on paper, where I have int pipe and I have array of 2 file descriptors, and I get the write end and the read end of the pipe. And then I said that the fork command is the command we use to create multiple threads or multiple processes. So I do PID is equal to fork, and then I go ahead and print out the return value of fork and the process identifier for the process that I'm currently running as. So I'm basically forking my process. I said fork is going to return twice, once to the parent and once to the child. And the way we know the difference between the parent and the child is the parent is going to get returned with the child's process ID. The child, fork returns a value of 0. So the reason the fork can return the value of 0 for the child is the child can ask for its parent process ID. A child only has one parent. But a parent may have multiple children. So when you call fork, the parent's going to get the child ID, the child is going to get the value 0. And that's how we determine whether or not we're in the parent or the child process. So what I expect to see is because I have the line fork, and I know fork returns twice, once to the parent and once to the child, I expect printf on line 25 to print out twice, because I now have 2 processes running this code. I have the parent process and the child process. So I expect this print line to happen twice. And then if the return value is less than 0, I failed, print out an error. This should never happen. If my PID is equal to 0, I'm the child, so I'm going to call the function child and send in one side of my pipe. And if it's a parent, I'm going to send in the other side of the pipe. So I'm basically creating 2 processes. One process is going to call the parent function, one process is going to call the child function. And then if I look at the parent function gets the read end of the file of the pipe, and it's going to read from the pipe, and it's going to print out message. The child is going to write to this pipe and say hello world to the parent. So the child's writing to this pipe, the parent's reading from the pipe. It could have gone the other way. And then I'm going to have the person who's reading from the pipe print out the message. Yeah?
So if it go the other way, would you have to change the arguments of the function so that one of them would have right?
Yeah, so if we see that the child gets pipe ID of 1, so the pipe ID of 1 is the right side of the pipe. So whoever gets index 0 gets the read side. You have to read from 0. You have to write to 1. So as long as you make sure the read and write's correct, you're going to be fine. So yeah. So output stream terminal is the same idea of a stream. It's the same technology as a pipe. The only And yeah, it's almost identical in the idea that you have one process and you're writing to a different universe that is like the shell or whatever you're writing out to. Yes, exactly the same. So I'm going to GCC pipe.c, run a.out, and what do I see? I see that the first thing I see is I see fork 350 equals 357. Second thing I see is I see fork equals 0. So I see the fork line actually prints out twice. Even though I only have one printf that says to print out from the fork, it prints out twice. The first time, the ID is 357. That tells me the ID of my child. So the parent process says my child process ID is 357, and we can see on the child, its ID is 357, and the parent's ID is 356. So we see that line gets printed out twice. We see 357 actually exits. So at the very end of the program, right before return 0, I have its process ID printing out and then saying it's exiting. So I actually write to my pipe. I write the information, hello world, and I actually exit my process. I'm done with my process, but I've written that data to the pipe, so that data needs to get read. And once 356 gets to run again, it reads the message and prints out hello world. So we're sharing data between two processes. Yeah.
So if you like called fork like
Yeah.
how would you differentiate between the two programs?
So if I call fork 2 times in a row, so first, so I'm going to modify this code to do that. So first, how many times is second fork going to print? Yeah, because fork returns twice, right? And the second forks in each of those are going to return twice. So if 2 forks in a row, it's actually going to return 4 times. The pipe may or may not, whoops, double declared this variable. So my first fork is 0 and 366, right? My second fork returns once, twice, 3 times, 4 times. So you have to kind of keep track of kind of what's returning. So you always know the child's going to return 0. So if you've got, you basically have a grandparent, 2 parents, and 4 children now. So you kind of have to keep track of who's, or sorry, no, a parent, sorry, a grandparent, 2 parents, and 2 children. No, sorry. The tree, I haven't thought about this. The tree actually looks, so you have this original process here. So this is your main. It forks and creates a child. Then the second round is that's going to fork again and create one, and that's going to fork again. So this is the process tree of your code. So it gets complicated fast, right? So it prints out 4 times, there's 4 processes. The actual relationship gets really complicated. It's always going to be a tree structure, but figuring out what that tree is and maintaining the state is hard. Like it's going to be really tough programming. We're not going to make you do that. Yeah, Matt?
I'm confused about how fork return twice. Like, does it return an array, or how does that code, how does it print out on twice after fork returns twice?
No, fork literally clones your entire process. You literally make a copy of yourself. So basically, it's like if you walk through that door and you got a clone, 1 of you walked in, 2 of you walked out. And now if the next thing you were going to say was hello, there'd be 2 hellos being said, right? It literally makes a copy of you. So you have literally 2 copies of that program now running. Complete identical copy, complete clone. So pipes are one way that we can communicate. They're a stream-based form of communication. So if we want to communicate a stream of data, that is done with a fork, or sorry, with a pipe. So second form of inter-process communication is we can also create what we call shared memory. So in the previous example with pipes, you had a read end and a write end of the pipe, and you actually wrote and read to the pipe. It was a stream-based form of communication. Shared memory is a completely different universe. This universe, you actually write to memory just like it was malloc. So basically, shared memory is malloc, but shared between processes. So if you don't want to use malloc, and in fact, I think we probably even, there's a little note in the malloc MP that you cannot use a system call called mmap. So mmap is basically the malloc for shared memory. It takes a whole crap ton more arguments than malloc. Malloc, you can just say malloc the size. So this is all you need for malloc. mmap, you have to give it a pointer of a suggested space you want, the size, the protection, the flags, a file descriptor, and an offset. You have to give it a whole bunch of stuff. But essentially, it also returns a void pointer. So any line that has mmap could have been a line that was just malloc. It works the same way as malloc. It gives you the memory address where your data can go. It's functionally equivalent to malloc, except for it can work across processes. So if I look at mmap.c, I have code that does that as well. So what I have in main here is, I copied and pasted some code. So let's get rid of those pipes. We're not using pipes. So what I have in main is I have a char star pointer that says mmap of 100. That's a linked field. I set up all the options, showed shared memory, and I can read and write to this memory. So it's shared memory that everyone can read and write to. So I've set up this malloc, and I went ahead and printed out the pointer just so we know where the pointer is. And I set the first byte of the pointer to be a null, so I can use it as a string. And I'm going to go ahead and do the same fork, and I'm going to call the child and the parent with that pointer. So I basically have one pointer that I used mmap. I forked that memory, forked it, and because it's mmapped memory that's shared, even across the fork, even though they have separate page tables, those pages actually point to the exact same memory in RAM. So now we've mapped two pages to the same physical RAM. So they're both looking at the same RAM. And then the parent and the child both call job. The parent starts at capital A. The child starts at lowercase a. And all they're both going to do is they're basically going to, they're going to append to the buffer. They're going to concatenate strings with their letter. So the parent thread is going to concatenate the capital A, then the capital B, then the capital C, then the capital D. So the parent thread's adding A, B, C, D, E, F to the string. The child thread is adding lowercase a, lowercase b, lowercase c, lowercase d. And because I'm actually accessing a shared resource without synchronization, there's a small chance they're running at the exact same time and can overwrite each other. So just without adding up 50 more lines of code to this, I add a small sleep to try and make sure that they get separated a little bit. So this is bad code. It has a race condition where you have two threads accessing a shared resource at the same time, or two processes in this case. So this could go bad. We could see some loss of data. It should be very unlikely because I've slowed things down. So basically, the parent thread is adding ABCD capital to the string. The child thread is adding lowercase ABCD. We're doing both of these at the same time. And let's see, if I gcc mmap.c and then run ./a.out, I see that they do drift a little bit, that I have all of the capital letters and all of the lowercase letters. And at the very end, I get lowercase yz at the very, very end. So it seems like the child thread was a little bit behind the parent thread. because they are running independently. But you can see all of the letters get written, and they all get written to the same memory. Because that is, IMMAP allows us to share memories across processes. And to really demonstrate the fact that this is not just what usually happens, let me replace the pointer with malloc. So I said IMMAP is just malloc. So I have malloc of 100 instead of IMMAP of 100. Recompile the program. And if I just use malloc, they're two separate processes. They have separate private memory, right? So if I just use malloc, I just get all lowercase letters and all capital letters. I have to use IMMAP to actually share the memory. So IMMAP creates memory that can be shared between multiple processes. So if there's data you need to communicate with, you will IMMAP a region of memory so both processes can access it. Yeah? So threads are always going to share resources, right? Processes, the only way to share memory with a process is to create an IMMAP.
Got it, but using the map is basically just like making the process act like a thread.
No, it's making a small amount of memory within that process shared between two processes. You don't share your entire virtual address space. You only share these 100 bytes. This is your only shared amount of space. Yeah. Yeah, if you used to IMMAP, now those 100 bytes of memory or whatever you're sharing is completely public to the other process, right? But everything else should still be private, because basically what's happening inside the system is, remember we have these, your virtual page table maps to a physical page, right? Basically as a pointer to where the actual data is. All the IMMAP does is essentially setting two pages pointer to the same location. So only for that page or that 10 page or however much space you need are those two pages actually pointing to the exact same location. Yeah?
So basically, you wouldn't put anything in that page like that you wouldn't want to be shared or vulnerable. So like you get the best of both worlds with threads and processes by having like some sort of shared memory, but without those security vulnerabilities, because you're only giving them like the stuff you want to share there.
Yeah, exactly. You're just giving a tiny little window into your world. Yeah. But you add a lot more complexity, because like this is a lot harder to write than malloc. Yeah.
Is the proc argument for IMMAP, is that the same like protection level, CPU protection level concept that we covered earlier?
No, this is memory protection level. This is like what page, how you can deal with that page. Yeah, so it's, can you make that page readable, writable? So you can make memory that only other people can read. So you may want to be like, okay, I'm the coordinating process. Only I can write to it. Everyone else can read to it. So you may not want any of your child processes to actually change the data you wrote. Aaron. Does what? Is IMMAP more expensive than malloc? Honestly, I don't know. So I actually think the most recent implementation of malloc that I saw from the Linux kernel actually calls IMMAP internally and creates private IMMAP pages. Yeah. Yep. Yeah. No. Well, if you get like really deep into how like how systems have completely optimized malloc, you're completely right, Aaron. That internally, we talk about this one big heap. You can actually do hacks where you don't have to use one big heap, because IMMAP will let you split up the heap space. So yeah, there's optimizations around everything we've done, but the base reality of it is sort of everything we're doing is how things work by default, and you can optimize the crap out of it if you want. But the optimizations are really there just to increase speed and performance, and it doesn't change anything foundational. Because IMMAP, what you do with IMMAP can get complicated really, 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 really fast. So even if you take like 423, the operating systems course, you won't even go into IMMAP. IMMAP is one of these things that like a few people use, but it's super powerful. Yeah.
Why is the first parameter of IMMAP null?
So IMMAP basically, there's not realloc like there is for malloc. There's not like reimmap. So if you wanted to reallocate memories that you've already allocated, the first parameter is actually the pointer that you did have the memory located. So if you wanted to use immap like realloc, you have to use that first parameter. Yeah, and if you look like the last parameter 0 and 0, like immap has a ton of different options. It's crazy complex. So that's your second form. So we have pipes that are streams. If you want to send a stream of data, you have the ability to share memory just like you have shared variables inside of two processes. So we have two universes. We have streams that are done with pipes. We have shared memory that's done with malloc, or done with immap. The third main form of communication is we can communicate via signals. So signals are a whole different form of communication. It is an interruption to another process. So signals are a way to interrupt the current action of another process. So signals are kind of these magical things. The actual system, often signals are used to actually kill another process. And in fact, the command line program you can use to send a signal is the program kill. So I can do kill minus L to list all the possible things, all the possible signals I can send this system. So here on this version of Ubuntu I have a whole bunch of different types of signals that I can send. And does anyone know what signal? So Control-C actually sends a signal. It sends an interruption to a process when you Control-C something. Does anyone know what Control-C does? Yeah. Does not send a sig term. No, sig term is like a really aggressive signal. Sig term basically says kill it no matter what. Yeah, Aaron? Sorry? Oh, keyboard interrupt. It is a keyboard interrupt, but the signal itself, it's not SIG-abort. It is not sig-seg-v. It's not segfault, but the segfault is a signal. So when you get a signal, you actually get a sig-seg-v, which that's signal number 11. Sig-seg-v, that's a segfault. So when the OS actually, we talked about exception handlers inside the CPU. What the exception handler will do is say, hey, you're trying to access a page. I can't load in that page because you don't have permission to that page. The way it notifies your process that you're trying to do something illegal and generate a segfault is actually through sig-seg-v. So it sends signal 11 to your process and say, hey, you committed a segfault. So sig-seg-v does happen, but that's a segfault. Yeah. It is sig-int. Yes. Did you Google it? No, you knew that. Awesome. Yeah, sig-int is the signal for a keyboard interrupt, sig-interrupt. So it's kind of your default level interrupt. So Control-C simply sends, is the same as saying kill minus int for sig-int to your process identifier, like 427. So that is the same as doing a Control-C if your PID is equal to 427. So we can send a sig-int to a process. We can also send a signal with a C call. It's also called kill. But the thing that's really, really useful is we can actually control what happens when our program gets a signal. So by default, default actions are specified for every signal. We can override most of them. So we can override most signals that are sent to a process. And we can do that by Sig Actions. Sig Actions says, let's change what we want to do when we receive a signal from the operating system. And you can override most of them. One notable one is SigTerm. I think you mentioned SigTerm. That one we can't override. SigTerm terminates your process no matter what. We can't change the behavior of SigTerm. That's the one. I think that's true. It's either SigTerm or SigKill. I'd have to double check. I think it may be SigKill. Maybe term's the nicer one. But one of them you can't actually modify. I think term may be, hey, terminate. Kill may be like, you're dying no matter what. Most of them you can modify. So what this means is, I don't want you to, what if I want to make a program that you can't shut down with Control-C? So we said that Control-C is SIGINT, right? So if we modify the default behavior of SIGINT to no longer kill my program, I should be able to prevent you from Control-Cing my program, right? Well, I might have done just that. So here's my Sig action. The Sig action, I said I'm going to, my handler is going to be handle SIGINT, and I have no flags. And I'm going to set my signal action for signal int to be my new action. So I'm replacing the action of SIGINT to this new action. And then I'm going to get myself in an infinite while loop. So I'm taking SIGINT, replacing it with the function handle SIGINT. And handle SIGINT, if we look at the parameters, it's a void function that takes an integer. So I have a void function that takes an integer called handle SIGINT. And I have it printing out can't Control-C me. So if I run this, gcc sigaction.c/a.out, it is stuck in an infinite loop, right? It's in my while one loop down here. Program's not going to do anything. Well, crap. I have an infinite loop. So Control-C. I'm stuck, guys. I've replaced the default action of SIGINT, which normally kills my process, with a signal handler that says can't Control-C me. So whenever I interrupt my infinite loop with a signal, my code jumps to the signal handler and handles the signal. So no matter how much I Control-C, I am stuck. I can't Control-C out of my program. Yeah? What if I forked around Control-C? I mean, then I just created like 1,000 processes there. Yeah, no, I mean, you can do whatever you want in your signal handler. Yeah. So if you want to Control-C, yeah, if you want to be violent, you can be like, oh yeah, every time you try and kill me, I'm going to expand. I'm going to grow. So now, if I want to kill this, well, I might have to go to another terminal, ps-aux, and say, okay, which program is running a.out? So PID 392 is handling that program. So if I do kill minus term to terminate 392, okay, I got out. I was able to terminate that process. Yeah.
So like, just about the, could you do
Yeah, yeah, yeah. If I go back here, yeah, I totally can. So if I run .a.out, if I want to just get the line, I can do ps aux minus grep a.out, and I can see that the grep command itself is printing out because it's obviously a running program. But then, yeah, I see now it's 456. So to kill that program, I need to terminate 456. And I was able to terminate that program. But what I did was I installed a signal handler, and that's a third form of IPC, is I have signal-based IPC, where I can interrupt the current flow of the program to send a triggered event. Those events allow you to trigger something when some event happens. So if you want to communicate something happened, you can do that. And if there's a bunch of default signals that the operating system defines, but then there's a bunch of user signals that are defined for, so basically everything, the sigmin, and sigmax, and sig user are all signals that are just undefined by the operating system that you can use for any purpose on your own program. Yeah, Aaron. Oh, so if I fork, then create the signal, which process gets my signal? So that more has to do with the shell, because the program that's actually running here, the actual command prompt, is just called a shell. And the shell is the one that's redirecting the signal to whatever's the running program. I'm going to guess it redirects it to the parent. I'm not 100% sure. I'm guessing your child doesn't get the signal. Yeah. Correct, correct. Generally, you can only signal your own programs unless you're root, and then you can signal everyone. Yep. No. Generally, you have to have the same, you have to be in the same permission group to be able to send signals to each other. The OS is not going to just let you randomly go and kill every single program. So in fact, I'm so sure of this that I can basically be like, okay, let's find a program on this Linux box they don't really need, right? So let's see, this process, I don't know. Let's see, I'm going to kill a root process just in case I have like special privileges here. So kill minus term of this process. So I tried to kill a process that I don't have permissions for, and it said operation not permitted. So there's a permission structure that exists. So I can't just randomly kill a process on this Linux EWS box. Yeah.
To answer the other question, I think it depends on what signal you send, because I looked up the difference between like SIGINT and SIGKILL.
Yeah.
SIGINT will send that signal to the parent but not the child, but SIGKILL will send that signal to direct signals about the parent and child process.
Oh, interesting. Okay, awesome. So it depends on kind of how depends on the signal. Awesome. Was that it?
I also had another question. What if you took the idea of like every time you take control C, it forks a new process?
Yeah.
Do it where every child forks itself, and you just have like infinite forking, or does the system?
I mean, so if I were to do while one and just do fork, I would probably crash my entire computer. Let me, after lecture, after I stop the video so I don't lose the recordings, we'll do that as the very last thing. Because I literally think this computer may just shut down. Like, it is something that's dangerous enough that I don't even want to try it out. But we'll try it. I'm going to reset so I don't even accidentally run it. Like, yeah, because you're going to create an infinite number of processes on your system. The only thing that might save me is this actually running in running in WSL, so it's in a virtual machine. So that may be the one thing that saves my system. It may just crash my entire Ubuntu, yeah. We'll see what happens. Should be interesting. We'll do that at the very end. So those are the three kind of main forms of IPC that you see within a single computer. So there's two other forms of IPC that you see within one computer. The fourth term of IPC is, so we've already talked about pipes, which are stream-based. We have shared memory, which is memory-based. We have signals, which are interrupt-based. So we have 3 different ways to communicate between processes. The 4th type is called a message queue. Message queues are really not used anymore. Like, I have literally not programmed a POSIX message queue in probably 15 years. So you basically can open a queue, you can give it a name, so you can basically call this queue like CS240 or something. You can send a message to the queue and you can receive a message from the queue. It's basically just like a pipe, except for it has like an ordered linked list of messages. And then you can close the queue. I think I wrote it once, like when I was an undergrad or something, and haven't written a queue since. Like, it's just not, I think it used to be used a lot. I don't see this queue stuff used very often, but it is a form of inter-process communication through a named queue. I don't know why you wouldn't just use a pipe. Yeah. I don't know the history. Yeah, does it predate pipes? I actually have no idea. I feel like no, because pipes were around. Yeah, I don't know. I think part of the queue, the problem is you have to have this magic queue name. I don't know. It's not, they've kind of fallen out of favor. I'm not exactly sure why. 5th form, semaphores. So I will say the one thing that semaphores kind of have going for them is mutex locks and conditional variables can't be used between processes. They're a thread-only thing. Semaphores, you can actually have a semaphore shared between multiple processes. Now, not only do you have the complexity of this magic number that might go up and down being shared between different things, it's now shared between multiple processes. You guys already know my thoughts on semaphores. They're a hot mess. They make your programming more complicated. I don't think they're even necessary here, but this is the one thing that semaphores has going over it, over mutex and conditional variables, is semaphores can be shared between processes. But I want to go to the main form of IPC that you're actually going to be using for the rest of this semester. Pipes are important, signals are critical, shared memory is really awesome, but the main form of IPC, 99.99999% of all IPC done, is done over a socket. And sockets are a stream-based connection to a remote host. Because most of the IPC that you're going to do in your life is not actually talking to 2 processes on a single computer. But most of the IPC that you're going to do is you're going to talk to another process on a different computer. So the other 5 mechanisms I've talked about so far has to be done on the same physical computer. It's great to communicate between, it's what you need to do to communicate between processes on one computer. As soon as you have a process on another computer, you have to communicate it with a socket. They are stream-based. So because they're stream-based, this tells you that you are going to be doing reads and writes. It works just like a pipe. You're going to read information or write information from a stream. There's 5 different calls that we're going to care about. So whenever you want to create a new socket, you do socket. Whenever you want to bind it to a particular port, which we'll talk about ports in a couple of lectures, you bind it. So you might say that I want to listen to port 24,000, for example. So 240 with some extra zeros. So I need to bind it. If I want to connect to someone else, I call connect. If I want to listen for an incoming connection, I call listen. And once I have the incoming connection, I'm going to say accept. So that accepts my incoming connection. So these are the 5 calls you're going to use. And what this does is it creates a socket that allows us to begin to do networking. So networking is basically what the second half of this class relies on. That what we're going to do after we go through all of the low-level systems is we want to talk about what do we expect to get out of networking. So when you send a message on your phone, what do you expect for it to happen? Yeah. Yeah, you want the data to be sent, so you expect data to be sent to another device. And you don't want just the data to be sent to another device. Do you want the same data that you wrote to be sent? You don't want like some zeros and ones to get changed around, right? So what we actually expect in a network is we send data to be sent to another device reliably. And reliably is the key word. Because there's a whole bunch of stuff that happens with networking. Because for your cell phone to get to a server that possibly exists in Europe, you're going to have a number of different hosts. You're going to have routers. You're going to have links. You're going to have apps that run it. You're going to have to use protocols, hardware, software. There's going to be bit errors. There's going to be packet errors. There's going to be link failures. There's going to be node failures. There's going to be delays in your message. There's going to be packets that are received out of order. There's going to be potentially governments or other people eavesdropping on those packets. And that's just a small list of all the things that we have to deal with networking. It is no longer do we have a single device that just happens to, we can control everything. Now we have a whole bunch of devices out there. And we have a whole bunch of people who might be spying on what we're doing. And how do we keep all of the data transmitted as fast as possible and as securely as possible so we get reliable transmission from the message you sent to the message you're sending to someone else? How do we guarantee they received it, and how do we know they've received it? And the way we do that is we define protocols. We define protocols, which are a message format and rules for exchanging messages. So we agree on a set of standards that if you communicate with me in this way, following these rules, and in this format, I know what you're speaking. So even if you're a cell phone I've never seen before, as long as you follow the same protocols, we're all going to be able to understand each other. So one thing you can see is if you're on a Linux machine, you can use TCP dump minus X to get a dump of all of the packets your computer is sending. So if I go to waf.cs.illinois.edu, my website, and I do a hex dump while visiting that website, the first packet that's sent of meaningful information is this packet right here. And this packet right here contains IP data, and I can tell you, and we'll talk about what all of those individual bits mean, because these are just zeros and ones represented as hex. That's the IP part of the packet. Then there's something called TCP. That's the TCP part of the packet. And then there's something called HTTP. And that's the HTTP part of the packet. So these are common protocols that we agree to use so that we can speak to each other. So in the last minute, I want to show off the last code example. So I have socket bind listen accept here. So socket bind listen accept. And what this should do is it should listen for an incoming connection on port 24,000. And it's just literally going to read out whatever's coming in that packet and then print out whatever's coming in onto my console. So I'm going to gcc socket.c, then I'm going to run a.out. And what this is going to do is it's now listening here, and it's waiting for me to make a connection to port 24,000. So I'm going to go find a web browser. Hi, AdBlock. Thanks for updating. And I'm going to go to localhost and go to port 24,000. So this says I want to go to my own computer. Localhost is the name of your own computer. And I'm going to go to port 24,000. I'm going to press enter. And Chrome just sent a packet. It sent 661 bytes to my web server. And it asked to get the page located at / using HTTP 1.1 on localhost 24,000. So what we just did was we just received our first bit of information from a completely different system. And this was in Windows. This is actually running in WSL. Two completely systems now are communicating with each other using the HTTP protocol. We're going to dive a little bit more into HTTP protocol and finish up other bits from Act 1. We're going to completely wrap up Act 1 on Thursday. I'm going to have a practice exam for you available by tonight, as the midterm is coming up next week. We'll talk full details about the midterm on Thursday. I know I promised on Slack to talk Tuesday. I'm finishing up just a few last questions for the midterm. Going to have the practice exam available for you tonight. We'll talk full details about the midterm on Thursday, but it's basically the homework questions and one practice problem. So let me know if you have any questions. I'll be here after lecture, and you guys are free to go, but if you're interested in me trying to crash my computer, I'm going to do that real fast.